Hey geometry students, welcome back. In this video, we're going to be taking a look at some examples of problems related to chords, secants, and tangents. Some of these are going to have very obvious answers, and some of them the answers are going to be a little more difficult to develop. We do have one proof here, that's letter D. And then some other problems that are sort of based on that proof, but sort of just based on the geometry of chords, secants, and tangents, mostly chords. All right, let's get started. Letter A, we need to identify each line segment or each line that intersects a circle. Well, okay, so let's take a look at this. I know that FG is both a chord because it has endpoints on the edge of the circle, and it's also a diameter because it passes through the center of the circle H. So FG is a chord and a diameter. Letter L is a secant because it is a line, so it can't be just a chord anymore. It's an entire line. It's a line that intersects the circle at 2 points. M is a tangent because it only intersects the circle at just barely 1 point. It just barely kisses the edge. And then this point here is not labeled, but it is the point of tangency. We don't have to identify it because it doesn't have a letter label, but I'm just going to say this is the point of tangency for line M and circle H. So let's just see if we've got them all. FG is a chord and diameter. M is a tangent. L is a secant. All right. Determine the value of A for letter B. Well, let's just go back to our slide that had our theorems. And let's see, if a diameter is perpendicular to a chord, then it bisects the chord. Here we have a diameter. I have a segment that has endpoints on the circle and passes through the center. And notice it's perpendicular to the chord. So therefore by theorem 43.1, we know that this chord is bisected by this diameter. They're perpendicular. And therefore, A equals 7. Let's just make sure we've got that right. Yes. All right, and the value of x here. Well, here I know that I don't know what the angle measure is, but I know that my chord is bisected. That sounds like theorem 43.2. If a diameter bisects a chord other than another diameter, well, this chord is not a diameter. This is a diameter because it has endpoints on the circle and passes through the center, and it's bisecting this chord. It's splitting it into two equal parts. So therefore, my value of x has to be 90 degrees. So 90 would be x because it's 90 degrees. Letter D is one that's just, it's a lot of nitpicky definition. It's one, this is a proof where you want to skip some steps because it seems like you can skip some things. But I'm going to go through it thoroughly and state everything that really should be stated to prove that CD bisects EF. And what we're doing in this is we're proving theorem 43.1. If a diameter is perpendicular to a chord, then it bisects the chord. We're not proving the part about the arc because remember there is also that and its arcs. We're not going to prove that. We're just going to prove the chord for now. All right, so we need statements and reasons, and we're going to start with the statement that CD is perpendicular to EF. Okay, that's something that we're given right here. And then, if they're perpendicular, I'm going to state that angle CME and angle CMF are right angles. That's the definition of perpendicular. Next thing I'm going to do my best on this. Don't judge. I'm going to try to make these triangles. I'm just going to add in 2 additional segments here. Hey, that's not bad. Okay, so I added in 2 additional segments. And the reason I did that is because next I'm just going to say that CME and CMF are right triangles because they both have this right angle here that we just stated in the last part. If they're right triangles, I can use any right triangle congruence theorem to prove that they are congruent to each other, and that might help me out. So let's do that. First of all, I know that CE, this measure here, is equal to CF. How do I know that? Well, a circle is defined as all points that are equidistant from a center point. Now, one of the things that I wish was stated here, it's a given because it's in the diagram, but it would be nice if it was stated as a given. I probably should have done it earlier. C is the center of circle C. But that's sort of redundant because it's pretty obvious. Um, but so you can see C is the center of the circle, and therefore the distance, any radius is going to be equivalent to any other radius. It's going to be the same distance. And that's just the definition of a circle. So CE equals CF. And now here's one of those nitpicky things. I really have to say they're congruent. I can't just say that they're equal. So I'm going to restate almost, but in this time I'm going to state it in terms of congruence. And that's the definition of congruent segments. Okay, so what do I know? I know that these are right triangles, and I know that CE and CF are congruent. The hypotenuses of these triangles are congruent. What else can I say? Well, I also know that CM, which is part of both triangles, is congruent to itself. That's the reflexive property of congruence. And therefore, now that I know the hypotenuse and one of the legs is congruent, I could say that the triangles are congruent by the hypotenuse leg right triangle congruence theorem. Okay, so I know that these two triangles, these two right triangles in here are congruent. What else can I say? I could say that EF is congruent to MF. That is corresponding parts of congruent triangles are congruent. And then I can say that EM equals MF. Definition of congruent segments state tells me that if I have congruent segments, then the measures of those segments are equal, and then that's the definition of a bisector. A bisector splits something into two equal parts. A bisector, a segment bisector splits a segment into two congruent parts. And that's what I've proven. I've split the segment EF into two congruent parts. Therefore, CD bisects EF by the definition of a bisector. It bisects EF at point M. I should almost say at point M here, but you understand what's happening there. All right, so that's how you prove that the first part of theorem 43.1 is correct. Now, let's consider an actual problem that we need to do some work with. If a circle has a diameter 9 inches and a chord that is 5 inches long, what is the distance from the chord to the center of the circle to the nearest hundredth of an inch? Hey, let's use, for E and F, we're going to use this diagram as if it's a diagram for these two problems. So a circle has a diameter of 9 inches. Well, if it has a diameter of 9 inches, that means it has a radius of 4.5 inches. And do I have any radii drawn on this circle here? Well, I have three radii, CE, CF, and CD. All of those are just 4.5 inches. Okay, so I'm just going to put 4.5 there. And we know that that's also the same distance as CF. Okay, so if that's 4.5, and let's see, I know the chord is 5 inches long, but wait a second. If a chord is 5 inches, that means that this little side of the chord has to be 2.5 inches because the chord is bisected by this line right here, right? Um, so this is 2.5. This is 4.5. Can I figure out what this distance is from the center of the circle? Sure can, using Pythagorean theorem. So let's go ahead and open a calculator and do that. So I'm going to say that 2.5 squared plus b squared equals 4.5 squared. And wait a second, I'm just going to do some math here. I need to get b squared on a side by itself. So what I'm actually going to do is I'm going to take this 4.5 squared and subtract 2.5 squared from it, because I have to subtract that from both sides. So what I'm really looking for is the square root. So b squared equals this. So if I take the square root of this expression, that will give me 3.74. And all I did was I did the algebra on the Pythagorean theorem. You could have done that on paper and gotten the same thing. 3.74. And that would be inches from the center of the circle. Let's see if we did that one right. 3.74 inches from the center of the circle. Okay, so I'm just going to write out some work for that one so that you can see. The first most important thing is to draw a diagram of exactly what's happening. And then what we did was 2.5 squared plus b squared, which we didn't know. That's what we needed to figure out. Notice I'm not saying plus because the other side we know 4.5 is a hypotenuse. Hypotenuse has to go on a side by itself. I couldn't have put it on the other side. So this was the problem we worked. I subtracted 2.5 squared from both sides and then took the square root of 4.5 squared minus 2.5 squared. That gave me 3.74. And I'm just going to note that that was for letter E. Letter F is much the same thing. You're going to draw the same sort of diagram for letter F. Okay, so let's do that. Letter F. A water pipe makes with a 16-inch diameter. Okay, so we're dealing with the distance all the way across. Remember, that means it has an 8-inch radius, though. So that means that if I wanted to note it, this side is 8. This side is 8. And this down here would also be 8. But this is the important one to note. Okay, so here I have my radius. Just a reminder that I drew these two segments because they were radii of the circle, and they're also the hypotenuse of this little right triangle in here. All right, so we have a 16-inch diameter water pipe, 8-inch radius. The water that's flowing through it, it's this level down here would be the water level flowing through the pipe, makes a chord across the pipe that is 15 inches long. Well, half of that is going to be 7.5 inches, and that's the number I'm interested in because that 7.5 is halfway across the chord, and it makes my side of my right triangle there. If the water makes a chord that's 15 inches long, how close to the center of the pipe is the water? This is the exact same problem. So I'm just going to copy my work from the last one, but plug in my new numbers. So this is actually going to be, instead of 2.5 squared, 7.5 squared. And then instead of 4.5, this is 8 for my hypotenuse. And I'm going to need to change this equation. So it's 8 squared minus 7.5 squared. And then I need to find the square root of that to figure out what side B is. So B equals the square root of 8 squared minus 7.5 squared. Let's plug that in. 8 squared minus 7.5 squared gives me 2.78 inches. 2.78 inches. 2.78 inches. And let's see if we got this one right. Bam, 2.8. It says, did it say to the nearest tenth of an inch? How close to? No, it didn't say, but it got rounded to the nearest tenth of an inch. I prefer to round to the nearest hundredth of an inch anyway. All right, that's how you do these sorts of problems. You should be ready to go for next time.